Okay, so we're in chapter 11. Yeah, chapter 11 is about the same as your chapter 10. So it's not going to be as heavy as in chapter 9. Of course, again, make sure you read the objective of that. Of course, we will be, one moment, we will be covering, yeah, each of these points in our lecture right here. First, we will get into the circular runout, and the other one is a total runout. They're just a two-dimensional control. Yeah, we call it control because they control the these I should say like the feature, yeah, on the part in many different ways. Yeah, and then we break it down into many different like profile, circularity, perpendicularity, parallelism, so and so. So now we come into a runout. So another two-dimensional control again to make sure that we're manufacturing the same thing as we draw, yeah, and design. And we're going to keep all of the specification in our drawing while we do the machining, yeah. So another thing is a circular runout, and it's going to give you the composite control. So we call it the circular runout because you're looking at your circularity and also the coaxiality feature, yeah, at the same time. So we'll be dealing with a surface that's normal to the datum axis, of course, and it's going to measure the imbalance of the material on the side. Okay, so compared to the other, that's I'm going to show you as we go into the example. Yeah, it's a little bit difficult for you to be captured, so just listen to it. Total runout is going to be your three-dimensional composite control. Yeah, and of course you're dealing with your coaxiality, your circularity, and the straightness, yeah, and taper, profile, surface really in relation to your datum axis. Yeah, this you can have to do it in three-dimensional because dealing with the three different things. All right, so let's get into the very first one is your runout tolerance. Okay, so your circular runout, your symbol looks like this little arrow, yeah, 45-degree, two-dimensional total runout. You have a 2, and then your base connected to each other, and that's your three-dimensional tolerance. It's going to control all elements of the entire surface simultaneously, meaning at the same time. And of course, you always have a datum axis. And this is just telling you your common. All right, so we'll start talking about your circular and your total runout. Yeah, circular. So when you deal with a runout, we are going to take care of all these things that were listed right here. Yeah, of course, as we go into the example, you can be able to see them. So right now, just read it. You can be able to connect to it before you ever get into the example. So your runout tolerance, it can be applied. Yeah, you can apply that to any shape, and that is going to be around the datum axis. Yeah. Otherwise, of course, you're dealing with the circular, so you always have to have a center and axis. Yeah. So, and that's what's talking about here. Also to a planar surface that is perpendicular to the datum axis. Your runout tolerances can be assigned, yeah, either your features or the features of size. So we have only two things going on. One is a feature, the other one is the features of size. And this term, okay, it just confused a lot of the student. You can just go with feature and the size, all right? So that is going to make things a little bit easier for you. So runout tolerance always apply regardless of the features. It doesn't matter what the feature size is, you're going to apply, yeah, regardless of it. Your zone descriptors, your modifiers, yeah, neither one of them are acceptable. Meaning like you don't have to do modifiers, you don't have to do your descriptors. Then your runout tolerance, you're going to provide a composite, again, two tolerances combined together. It's a composite control affecting either the form, the location, orientation, and part features. We don't have anything more than that anyway, yeah, when you deal with the object. So you have your form, location, orientation always. all the features on that part. So whenever your runout tolerance is specified one or more datum, it's going to be required in that feature control frame. So of course, when you are reading like this, your brain is not going to get connected with your feature control frame, which is your little table identifying what's the tolerance, what is it that we're controlling. Yeah, here our control is a runout, followed by the tolerance, followed by your datum. Yeah, that's always there anyway. The only thing that change is your control. And then of course your runout tolerances are we will verify, yeah, doing the same thing, but the tool we're going to use a dial indicator. And of course you're going to position that dial indicator normal, meaning 90 degrees, yeah, to your control surface. And your part, since it is a circular, you can go 360 degree rotation. Yeah, so that's a pretty makes sense for all of that for runout. Okay, so your circular runout, we're gonna start getting into it. Again, don't forget the tool to verify. Yeah, so we use a dial indicator. So you have encountered many different, yeah, your comparator, optical comparator, where we can see the surface. Then for profiling, for circular runout, we're going to use a dial indicator, and we're going to see that, yeah, one by one. All right, then your total runout, we will use a dial indicator as well to verify that. And we're going to show you, yeah, each one of them in the example. So let's just keep going. Don't worry too much about it. And of course, your runout and your datum sequence, they have a relationship, so a specific relationship between your individual feature on that part, and they are definitely, okay, linked functionally. And they're also frequently greater significance than overall relationship. Yeah, overall relationship means we're talking about all the features on that part, dealing with the common datum axis. All right, you can't be able to get it right now. So let's get into the very first example, your runout and your datum sequence. So now we're going to spot, right here we have a different control frames right there, and the runout is right here. That's your angularity, your profile. Here's a total runout. Yeah, here is your circular runout right there. Yeah, and then here as well, here, and then here. So we go into each feature of that. So your functional relationship, the runout tolerance, yeah, of that diameter is reference to the datum axis C, and not your datum axis A and B. Okay. So A and B is actually showing you right here, which is a tie. This is a separate one, sorry. So A and B is right here, and then right there, okay, right here as well. See, and your C is a completely different thing, which is right here, yeah? Then we have DC, your AB tied here. So we are talking about this guy right there, yeah, datum reference C, which is here. So we're talking about this runout. And of course dots, yeah? And you deal with this two different datum. The rest of them are going with the white stuff, yeah? Now let's go into the multiple leaders. So here we are using a 2 liters line right there. And for this circular runout, showing you here little thing and right there, okay? You can't see very clearly. So when you study, make sure you make it really big, yeah, for this. Make it big for this position, so you can see the surface, yeah, which surface we are identifying for this runout, or controlling, I would say, with this tolerance 0.04, and that's your combined A and B. Okay. Application. So let's go into it. Your runout tolerances. So we usually use the runout tolerances, yeah, when we have to deal with the application where your part rotation is involved, because it is a circular runout, yeah. So we expect these rotation can happen. So the control got to be the runout, because you are dealing with the rotation, yeah, some of the part. So the designing parts like the rotating shelves, your cam followers, your pulley assemblies, and your bearing or surface are the example of parts in whose features may be controlled using total runout tolerances. Okay. Okay, then we also have to take a look at the runout. Yeah, is again same as a previous chapter is going to apply. Yeah, it's always applied regardless of your feature size. Regardless of feature size, your manufacturing parts, which have been controlled, okay, with your runout tolerances. That's a really bulky. All you have to understand is every time we deal with a runout control, we can be able to apply that regardless of your feature size. All right, that's all. Don't worry the rest of them for now. Yeah, we'll get into a different example. So the first one is to see the feature applicable to your runout tolerance with this part. So here we have two views. Yeah, one is this a front, and then this is a front, and then this is a side. Yeah, so you're looking at this thing like straight from the front. So your surface that is constructed around a datum axis, which is this guy, and we can be able to control with a runout tolerance. Yeah, because we're dealing with a circle here. So of course you expect the rotation around this axis. So including the surfaces that are perpendicular, because the surface is definitely perpendicular to that axis. All right, now we see, so look at that, the surfaces constructed around that datum axis. So yeah, datum axis is right here. These are all the surfaces. Yeah. Now you can also take a look at the top part of that, and thus your surfaces at your right angle, yeah, to the datum axis. So these vertical lines right there, okay, look at that. These are the horizontal, yeah, on top, right there, showing you. And then we're gonna apply different colors, so you can see this is your red line, okay, that's your white line. So the features used to establish your datum axis, all right, got to be design related. That's because when you look at the features that are central, yeah, to the manufacturer or assembly of your parts, and that's going to be like which is going to establish, yeah, in that axis rotation. So it's a little bit difficult for you to be able to see it. And I want you to just simplify by understanding every time you deal with a circle, there is some form of rotation which can happen around that axis. Yeah, if we have to put it in a common words for you. Then of course getting into the runout datum features, another one. Here it's just showing you your datum selection, yeah, got to be done by using one of them. So this is just a method like how we can be able to do this tolerance, yeah, for the runout control. So first you're going to think about, can the functional design requirements of the part be established, yeah, by using a single diameter of sufficient length and a planar surface at right angles to that. Then you're going to think about, can a single diametrical feature be used, right, to establish the datum axis? So if so, is the datum feature accessible, or is, does it have sufficient length to accommodate that manufacturing and verification requirements? Meaning, like by using this, control, can we be able to do the manufacturing and verification? That's all. So make sure that you put everything in your own word, which is easier for you, yeah, to be able to translate the whole thing like this. So then we will also look at the two diametrical feature, meaning like you're looking at a circle with a diameter anyway, and then you're going to think about whether they can be accessible. So do they have a sufficient length, do they have the sufficient axis separation, things like that. We'll look at it. So let's take a look at it for the runout. So here we're dealing with the runout with this tolerance, yeah, so the control is on that runout. And then you're going to have the A and B, because this is a runout, because when you look at it, this is your cylinder, yeah. So you're dealing with this axis, and when you look at it from this side, you're going to see the circles. So your planar datum feature A, yeah, right there, And then your datum B is going to be right here. Yeah, this is your tolerance. So your diameter, yeah, is going to from here to here. Diameter is 20.5 all the way to 21.0. So we're going to use that to locate the part, yeah, in the gauge to verify the Runout tolerance specification, which is 0.1. Okay, so we have two, primary and a secondary datum reference. Primary 3 point, yeah, secondary is going to be 2 points. So we can be able to use a gauge to establish these datum reference. Of course, we can be able to see, yeah, here is your datum feature A, because see that, yeah, it's attached to here for this surface right there. And we're in exaggerated mode, so we can be able to see the surface, see imperfection right there. Your datum feature B is going to be right here. Yeah, they are perpendicular to each other. So your gauge axis, which is this guy, is going to be your datum axis. And of course, in the diagram here, yeah, there's a note for this axis is your datum axis because of this two plane, yeah, gauging it. And our circular runout is 0.1 with datum A and B. All right. Okay, then we'll get into the next example where we're going to deal with the only single diametrical datum feature. So I'll show you. So here is your runout, yeah, circular runout dealing with this, yeah, cylinder here. So here is your axis, and then that's your datum axis. Your datum reference is E, yeah, from here to here for this diameter. So that tolerance is 0.5, which is based on that datum reference. So the datum feature E is going to be used to establish the datum axis. Yeah, we know that. So diameter, you have a single diameter, meaning like this is a single diameter. We don't have a two like in the previous example before. So you have only the single diameter of your sufficient length. Now we're going to gauge it. So we can see orientation, also the position of that datum axis established by that, yeah, datum feature, which is your E. And we can be able to get this datum axis E by that established by this datum feature E. Okay, so here is your gauge, and this is your circular runout, yeah, and that's a 0.5 based on the datum feature E, and which is your datum reference anyway. All right, the next one we'll get into the datum axis established by this time two diameters. So let's take a look at it. So the very first diameter is going to be, yeah, datum axis A and B, which is this and which is that, and that's your first diameter, and that's your second diameter. Okay, and of course you have total runout, and this is your singular, which is your circular, yeah, runout right there. And we're showing these surfaces. So the compound, which is this guy, because they're tied to each other. So compound datum A and B, yeah, A dash B, of course. So when you write it in this control frame, feature control frame is going to be established by selecting the two diameters, yeah, datum diametrical datum features, which is this and then that. And we're going to be that must be controlled, yeah, for the runout. Of course, every time we control, we know that it's going to be inside of this tolerance, yeah, zone. Right now I can see it, but there is a value in that, and that is your tolerance. And of course, these tolerances are relative, yeah, relative to these datum features. Right now we're using 2 diameters. For the 2 datum, and we call it the right here, yeah. Now we start to see the imperfection because they are deviating from the axis, yeah, measurement axis, your datum axis AB, which is your gauge axis anyway, where the measurements are verified. So your datum features AB, when mounted between centers, it's going to establish the datum axis. Yeah, we already did that again and again, so you shouldn't have any kind of problem doing it. And of course you have equal importance for your orientation and position. Okay, then we're going to gauge it. So that's your gauge axis. Your high points contacts are necessary because we're dealing with a primary, so you need 3 contact points. Of course, your datum features A and B, they are equally important because they're ties, compound, to establish the orientation and also position of that axis. Okay. Significant runout. We're going to review. So your runout is your composite, again, control. It's going to affect your form, location, orientation, and they're always relative to your datum, axis. And we're going to apply to the part feature, and it's always around a datum axis. So it will have a relationship with your datum axis. So you know that datum axis is necessary for this runout to be controlled. And of course, you need at least one feature control frame or datum reference. And you can be able to identify that in your feature control frame. So your runout, we have a maximum variation, and we allow that if your part is going to be mounted on that datum axis, so because we also deal with the rotation around that axis, your circular runout. You cannot modify, your runout. Why? Because if you do the modification, it's not going to be correct to use your diameter symbol, Okay, so let's see another example right here. So in this example, we have a datum, A, datum feature, and we're going to put it right there. Your runout is controlled by this tolerance, which is 0.8. And that runout is going to be this diameter right there, Axis is going to be right here. So this is your datum axis. Of course, each element of that part has its own unique center. So your circular runout is just an attempt to control, circular surface elements in relationship to this common axis. Okay, let's get into and gauge it. So when we gauge it, you got the gauge axis right there. So your datum axis A is going to be established by your smallest true cylinder right here. This cylinder is bigger than this cylinder, so we're going to use this, to circumscribe about that datum feature. And your control frame is given to you right there, circular runout with 0.8 tolerance, and your datum plane is going to be A. All right. Now we know that the circular runout tolerance is going to apply independently, for each of your cross-section circular element. It's a little bit difficult for you to be able to see it, but anyway, we are verifying from this, datum axis. Element mean like we're just looking at everything that is, for this diameter around this axis. Now we're going to diverge it, mean like a drawing it in a bigger, so we can, bigger diagram, so we can be able to see these imperfections, of that surface. So we'll take a look at the rotating around, 360 degree around that datum axis. So your diode indicator, which is this device, is going to measure, that runout. So that's going to be in a fixed position, normal, meaning 90 degree to that surface, Of course, you can see this with the naked eye. Thus, you need an instrument to be able to measure, and we are using the diode indicator to do that. So your metrology. And you can rotate, around that axis, 360 degree around. All right, then we'll get into here. Your circular element, element meaning like everything, these little points on that surface, got to be within that specified runout tolerance of 0.8 right there, Your full indicator movement, which is this guy, is called FIM, full indicator movement, and that's a 0.8 because the tolerance has got to be in that range anyway, So the diode indicator is in a fixed position, and again normal to that surface. All right, then let's get into the circular runout specification. So here, what you need to know is that we apply the circular circular Runout tolerance, and it's got to be at each measuring location, as the part is like rotated through 360 degree. So as you rotate, we are applying the circular Runout tolerance to each of the measuring location. Of course, your measurement device is your diode indicator. All right, so your circular Runout, your feature datum relationship, so we will take a look at it. So your Runout is nothing but it's just a surface, and we are dealing with the datum axis, control. So when you apply to the surfaces, constructed around an axis or datum axis, your circular Runout, you can use it, to control the cumulative variation for your circularity and then your coaxiality. Coaxiality is nothing but you're sharing the same axis, right? That's all. Anyway, right now you can't be able to see it when we talk about our full indicator movement, and then of course your rotation. So TIR is your total indicator reading, and this is your full indicator reading. So you have FIM, FIR, and then TIR, okay? And let's take a look at it with different examples. Okay, so example number 1 is going to get into this diagram right here, and your Runout right there, and your diameter is going to go from 24.0 to 24.4. Your tolerance is 1.0 millimeters, because you have a number right in front of the decimal. And so anyway, the axis, your datum axis is A, your datum reference or datum feature is going to be A right there, on that surface. Okay, so your circular Runout is going to control, of course, your independent surface, which is your circular surface anyway, because you're dealing with this cylinder, So when you take a look at it from this side, these are circles sharing the same coaxial, which is your coaxis right there. So your circular Runout, in this example, your circularity is going to relate to a geometric counterpart. That means like your datum feature, okay, they're never acceptable, because your Runout is going to relate the surface element directly to a required datum axis. So it's just this one right there. Your diameter is 8.4 all the way to 8.8, right here. Since you have 2 circles, one is right there and the other one is right here, 2 diameters, so therefore 2 circles. So they're not concentric, but again, you have a coaxial, meaning like you have the same datum axis. We already know that, we have been looking at again and again. Of course, so we're going to draw our zone, so we can be able to see the radius distant 1.0 millimeter apart, and then your axis is going to be here, that's coaxial, and then your center of your concentric circle. Concentric meaning a circle is inside of the other circle, which is this diameter and that diameter. So diameter of this body, diameter of the head, right? Sharing the same axis. Okay, then we're going to see our zones. So here is your FIM, and that's going to be less than or equal to 1.0, okay? Your FIM, again, is your form indicator movement. Don't forget these things. So if I start to use FIM, then you get lost. All right, so now let's get into different views, So this is from the side view that you can see your concentric circles right there, showing you the axis right here at the center. Your FIM, form indicator movement is going to be right in the zone. So it's got to be less than or equal to that 1.0 tolerance, And of course, that part is going to be rotated 360 degree around, measured by this, diode indicator right there. So you're going to position 90 degree, so that's a normal to the surface that you are measuring, which is your Runout. So your circular element of the part yeah, which is your runout, circular runout. And in the other view, you can be able to see, so that's a front view of this, okay? So we can be able to see this, yeah, in that tolerance zone right there, the surface. So we can be able to do this circular checks, yeah, as necessary to every time we do the check, we are verifying, yeah, verifying that specifications are met, yeah, in your manufacturing processes. Okay, so then we'll cut into the next one is your part. It's going to go your axis approximately about 360 degree, yeah. It's a little bit difficult for you to be able to see it, but we're just telling you that this is rotation, yeah, is happening, and it's a 360 degree. We rotate it. So on your dial, yeah, indicator dial on the gauge, yeah, this is your gauge. Gauge means we're gauging, meaning verifying these specifications. So, but of course, it is still within the required tolerance zone. And see, yeah, it is still in the yellow zone in this example, so we're fine. Okay, so the control of your circular elements, we already know that it's got to be within your runout tolerance zone, yeah, and your total movement of that dial, your measurement device, dial indicator cannot exceed your tolerance value, yeah, identified in that control frame. So that's what we're talking about here. So don't forget, these are the two, yeah, most important point for that. And then of course your rotation 360 degree going around that datum axis, yeah. And that got to be again 90 degree to the control feature, which is your surface that you are gauging. So the gauge is going to reset, of course, after you finish your complete rotation to do your verification, yeah, and that's for your each check-in location, which we already showed you right here, yeah. Then we'll go back to here, and make sure you go each slide very, very slowly to take in the new information. It will take some time for you to get it, trust me. Yeah, even the people like us who have to study takes like about 6 to 12, yeah, 12 months to be able to get that. You can't get it in like one semester. You have to read it repeatedly for you to be able to get all of that if you determine to stay in our line, yeah. Of course, the most important thing is you can't be able to go over your limits. So that's formally we write it like the limits of size cannot be violated. Example number 2, we have this yes, a part right here, yeah, a little bit different because your cylinder smaller diameter is on this side from the previous example, and we have a datum plane is going to be B, yeah, datum feature reference. So here is your circular runout, yeah, and we're dealing with this, yeah, tolerance zone, which is 0.04 for that surface, inclined surface. So your tolerance zone is your 2, again, concentric circle, because that's the circle, and then this is your circle. So your 2 concentric circles, and your center is going to be this, yeah, located on the same datum axis. So your radial distance, yeah, between these circles is going to go about 0.04 runout tolerance value. You should be able to read everything by now from the diagram. Of course, now we're dealing with the datum axis B, because our datum reference is right there. You can go the rotation, which is your revolve part, can go around like that. We're going to gauge it, so to make sure that your surface is going to stay, you know, within this zone. So your FMI is going to be less than or equal to your 0.04 millimeter, but not over. Yeah, these things you should get it one by one. Yeah, independent surface, and to that axis, your line element we can verify in this way by using the dial, yeah, indicator. All right, the next one, we're checking here this point and here that point. Of course, we're going to check it out so you can be able to see each, yeah, point check right there. So these are called the independent surface to axis, yeah, this axis, and we call that the line element. And what are we doing? We're using this instrument to verify, yeah, these points right there, so that they are inside of that, yeah, tolerance zone. Okay, and so now we Now we're gonna go into the next section. So before that, we're gonna wrap up with the control circular element. Okay, this is just a recap. So we already know about our rotation, 360 degree, our datum axis, we know that. And we also have to remember that your circular Rana always applies to the regardless of feature size. So these points that I just pointed out are very important, when we deal with the circular elements for the circular runout. Example number 3 is going to go into the next example with this diagram, which is going to be from here to here is 24.4. So your perfectly circular element, and you have your again datum axis is here, your datum reference feature or datum feature is going to be A right there, and this size is going from 8.6 to 8.8. okay, so that's about 0.2 difference. So then here your circular runout is 0.3 for the datum feature A. So this shank of that pin, which is this low pin, is your datum feature A, because this A extension is coming out from that surface. So when we take a look at the head of that, we have a circle here, circle there, and a circle there. These are all your concentric circles. So when we look at the head of that pin, okay, that got to be within the tolerance, which is 0.3. So make sure where you see the leader line, your leader is going to point out which surface, is a different example. So the third example is pointing right here to control that circular runout. Okay, now we're going to draw our concentric circle. So your circle is right here, and then your circle right there. So then your datum axis is going to be right here. Of course, there's a connection, the head, and then your pin shank is going to be connected with this body middle part right there. So the surface is going to line the element perfectly. So circular, and then you have your co-axis right there, which is your coaxial with your datum axis A in this case. So your tolerance is 0.3. Then we're going to gauge it. So put your dial indicator right here, and then we're going to start going this direction rotation. So when you think about the dial indicator, during the verification right here on this circular runout, what we can see is that indicator is going to be equal to 0, after completing one revolution, of course, of that part. So go from here to go all the way back to here. Your datum axis is right here, and then your feature axis, they're all perfectly aligned. See, doesn't have any variation from the center. So anyway, so let's go in there, and we're going to consider now the example where you have the center of that circular line, which is this one, is perfectly aligned with the datum axis right there. So the center of this circular line, and that's your datum axis, all right? It's aligned to each other, but that line element itself is not perfectly circular. Okay, now we are going to draw our zones. So your yellow, as usual, is your datum axis is right here, and your feature axis also, they are sharing the same axis, so we have a coaxial, and of course your datum feature A is going to be right there, because see where this symbol is standing on that surface, which is your smaller circle right there, smaller concentric circle. And then of course here is going to come into your true, true runout is right there, which is your this diameter right here. And then the zone, we can be able to see with the yellow zone right there. Okay, all right, then let's go into and see this circular element is going to rotate about 90, so going from here all the way to here, that's each 90 degree, altogether 360 degree all around. So that's your imperfect circular element, is a coaxial with your datum axis, so it's pretty imperfect in here. So when your part is rotated on the datum axis, but then it's rotating only 90 degree, but the out of circularity still within the zone, so therefore it didn't violate the Runout surface to your axis of tolerance. Now we're going to gauge it so we can get our indicator reading, which is your FIAE. So that's going to be less than or equal to your, where is my control frame here? Yeah, so 0.3. Make sure you always check your tolerance. Of course, you have different view, that view, which is this, and then of course you're looking at this, so you can see that, front is going to be here, and so the side is going to be this. So the part is revolved again around that datum axis, meaning like you can rotate this part. So the full indicator movement must not be greater than the Runout tolerance specified in the feature control frame, which is this guy, meaning can go over that tolerance zone. As long as it stays within the tolerance zone, it doesn't matter, even though it is imperfect circular element, we're still okay. So that's what it's talking about anyway. So at the lowest point of your measurement, on that non-circular surface element, because it isn't circular anyway, it's kind of like a D shape, kind of looks like a little bit of spherical. So the full indicator movement on that dial indicator got to be less than or equal to that 0.3, meaning like at one point it is 0.3, at the other point, see how this is like kind of going down like that, here is like going up. So the closer to the inside, lower limit of the tolerance zone. So that's what we call the imperfect or circular element, which is having a co-axis with the datum axis. Okay, now, and here, if you do a one revolution, that's a 360 degree around the datum axis, your indicator register out of circularity, no more than the Runout tolerance. Again, your permit, we always go back to our control frame, and that's a 0.3, okay? So it's just telling you that the indicator reading less than or equal to 0.3, even though you go one round. All right, then we see our tolerance zone right there, and of course we're going to bring our diameter, the zone, of course, here you can see less than or equal to 0.3, so from 24 all the way to 24.4. Yes. And of course we are going to do the verification check, and you'll reference your datum axis from here, and of course we're looking at this circular Runout of that diameter of the head. So because your tolerance is going to control that surface, so we can be able to see these verification is going to be made to make sure, to ensure that whether that part is within the specification or both size and location, the size and also the location got to be relative to that datum axis, okay? So here in the next example, we're going to think about the circular line elements. They are circular because they are circular line element, but their centers again is going to be this time eccentric, to the datum axis. So let's take a look at that. So eccentricity. So when we do the variable gauge, in order to verify, that got to be in contact with your datum feature, and that's going to be established by this datum axis A, and we're going to gauge it. Here is your datum axis. Of course, this time in this example, you have a circular non-coaxial, so therefore look at that axis, see, it's kind of off, they're not aligned to each other. So that's we call it the circular non-coaxial segment is happening right here, in your, so you can see the variable cylindrical gauge is right here, and the high points again, is going to be in contact with the shank of that pin. But again, it's kind of off, from this to here in this example. So you have a different axis. So you have a datum axis, which is that one, and then another axis is going to be right there, the blue one. So that's your axis of the eccentric, circular element. Okay, so here you can be able to see, the eccentricity of the head of the pin is shown right here, and of course it is exaggerated, so you can see the axis of eccentric circular element right there, and then your datum axis right here at the center, and you can be able to see the offset right there. And now when we go into this slide, your max is 0.002, and that's like this much far away from the datum axis, which is your gauge axis, and we can be able to see it in this view very obviously. You have a two axis right there, and they're not aligned to each other, so therefore they're not coaxial. Okay, now we're gonna bring in our circular element right here, which is which is shown. That circular element is shown at your extreme position of your eccentricity. Eccentric meaning like weird exit, It's just weird. It's not conventional. So that's your maximum offset from that datum axis. So now we're gonna bring our zone. The zone is right here in this view. You can see that, And that zones again is gonna be your circular element is still within that zone, so we're fine. The zone tolerance is 0.004. So your FMI is still within the 0.004 limit. Now we're going to bring our indicator to verify that. So your indicator is going to read less than 0.004 inches. We are in the inch system because there's no zero in front of decimal point. So your circular element, when you look at it, is still inside of that zone, which is 0.004. All right, then we are now going to go straight into it, and now it is reading 0, because see how it is different from the first example where that's like showing you at the max, right, but less than 0.004, but now it goes down. See, now it becomes your indicator reading is going to show you 0. So how sensitive these verification devices are, and they're very the best ones are, of course, developed, and it is expensive to buy them, but a regular one, of course, not that expensive, but again your accuracy is kind of off. But anyway, so we can go into the point check. So verification point check is here, so we'll be dealing with the FMI got to be less than or equal to 0.004, and if this is not satisfied, you'll be violating that. So when you do the check on your FMI, you gotta understand that if that check is going to violate your FMI, acceptance zone right there, and if it's going to violate, if it violated, then you would not accept that part, because it isn't acceptable. All right, then we will go into our concept review. When you have your diameter, it's going to be controlled by your runout, circular runout, your maximum, the maximum axis, its axis can be offset from the datum axis, and that max is only 1/2 of the runout tolerance value. So all you have to do is divide it by 2, and you will get your max. So circulating your minimum and maximum and minimum offset distances on surface, and we will control that with the runout. So let's take a look at the example of that. So here we see, when you look at this, we can be able to see the datum, is right here. So that's your diameter, and here it is going to be this diameter right there, and that is controlled by this runout point 2. And of course this big diameter is controlled by this runout point 6, and of course this diameter here, when you look at it, is controlled by this perpendicularity, and this one is another runout, which is this little diameter right in there, and that is controlled by point 1. So corresponding control frame showing you which diameter or circle that it is controlling. So in this exercise, we're going to calculate the maximum and the minimum distances from your x and y. So here in this case, your x right here, and your y that's here, and we need that distances. So let's see how we do it. So we're going to put it in a table so we can be able to see your x and then your y right there. And then of course we have our corresponding control frame. So first we are going to start calculating. So the very first one is 11.3, which is to find out that distance. So we're given from here to here, and then we're given from here to here. If you minus this from here, we're going to get both of that, and we're going to divide that with 2. So your minimum radius, which is this guy, that's your size tolerance is given here, 14.2. to 14.8 diameter. So that's a 7.1, okay? When you minus it, you get 7.1. And then we're going to minus your bigger diameter, which is 22 to 22.6. So when you subtract that, yeah, you'll get 11.3. And then we're going to subtract 7.1 to 11.3. You'll get 4.2, okay, here. And then you're going to divide that with 2 because you have this x, yeah, they're the same thing, same distance. So if you divide it with 2, you're going to get the x distance. So that's going to be 0.6 plus 4.2 divided by 2 is, yeah, 2.1. Then we are going to put the maximum of that. Okay, so before that, we are going to get into this tolerance. I forget to tell you about this, sorry. So 0.6 and also the 0.2, okay, add them up. And then we're going to divide it by 2, okay? This is dealing with the tolerance, not the size. That one is the size, all right, this. And then this one is just the tolerance. And then we're going to put in, the very first one is 4.2, and then we're going to add 0.4, which we get it, yeah, from here. So 678 divided by 2 is 0.4. So you're going to add that up to 4.2, and you're going to get 4.6. That's included the tolerance, yeah, don't forget that. And after that, we're going to reverse the process, and then we're going to get the minimum, yeah, distance between them. So first we're going to begin with your 22. So that's 11, and then we're going to do with the 14.2, 14.8, and you're going to get 7.8 for that, yeah? So here in this example, what he did, okay, is just a little bit different. So when you read it, if you don't understand, yeah, like how we do it, you can also go his way, yeah? So his way is a little bit different. You can do whatever way you want it. You can subtract this thing from here like I did, and then divide that with 2. You will end up with the same thing anyway. But here is what we're doing is like, what he was doing is like, you're going to take the minimum radius, which is minimum is 14.2, divide that by 2, so you get 7.1, right? And then you have your maximum radius is 22.6, divide that by 2, so you get 11.3. Okay, then you subtract it and you're going to end up with 4.2, and then you add your tolerance. So this is the author's way of doing it, yeah? So if you, but you can do any way you want it. It will come out the same thing anyway, okay? So you get 4.6 for that. All right, then the second one is going to be, you are going to take getting into the minimum. So therefore, we're going to take 22 instead of 22.6. Divide that with 2, we get 11. So 14.2 and 14.8, we're going to take the 14.8 for the max, yeah? Divided by 2, so you get 7.8. And then we're going to do the same thing, yeah? You will minus that, and you will get 3.6. And then we're going to add the tolerance, yeah, which is 0.4 by calculating the same thing. So when you subtract that, you will get 3.2. You have to subtract it because we're finding the minimum distance of that, yeah? Maximum, you're going to add it, so that we get 3.2. We're going to do the same thing for y, and you will end up getting 8.75 and then 7.65. And I want you to go slow for this calculation, okay? All right, then we'll get into the circular runout of a surface that is normal to the datum axis, meaning 90 degree to the datum axis. So now where I told you I'm gonna to explain this wobble, control the wobble thing in one of the example, and this is the one, where you look at the circular runout control on a surface that is perpendicular to your datum axis. So here we can see the perpendicular, right there axis, and this is your datum reference and or the datum feature. This is the same thing, we call it datum reference anyway. So here is your circular runout, it's going to be right there, and that's a 0.2. Your datum reference is A, right? And this one is a 0.1. Your datum reference is A as well. Okay, so we'll take a look at this another example for your surface perpendicular, to your datum axis. So this example is a little bit different from the previous examples that we're doing. So you have your flat surface on the left side of your this tool, which is your bushing, that's got to be perpendicular. So this thing's got to be perpendicular to that axis, so we can see very easily, there's surface and then that. Of course, we have a different control, which is your Runout control 0.2 and the another diameter, which is this from here to here. So that control is going to be 0.1 circularity, which is your circular Runout we're talking about. Meaning Runout mean like the whole thing. So that perpendicular the surface to that axis, your Runout tolerance 0.2. And we can read it. We can also see it very clearly. Okay. Then when you probe it, so another thing that we say probing mean we're using an instrument. In this case, is your dye indicator. So when you probe it with your dye indicator, meaning like checking the verification and verifying that you were brought into contact with your flat surface, and then we're going to set it to 0 to start, and then that part is going to revolve, right? Revolve means going rotation on that datum around that datum axis, 360 degree. So your flat surface, it's not going to be perpendicular to that axis. If that was the case, then the full indicator movement is going to detect a circumference where more material exists on one side than the other. It's a little bit difficult for you to say, imagine that. We're just looking at if the surface is perpendicular to that axis, and in order for us to do, you have to use the indicator, dye indicator, put it on, set it from 0, turn one around, 360 degree, turn one around, and if they are not perpendicular, you will have wobbling effect. Wobbling is your material of that part is going to be more in one side than the other. That's all. Can be able to see it. You just have to measure it to see that. So you will see the numbers. Measurement numbers going to increase up and down from that 0 point. So now we can be able to see that you're mounted on this datum feature A, which is this guy, your axis, your surface. We're gonna verify by using this dye indicator. So if you have a wobble, then your material is going to be more in one side than the other. And of course your perpendicularity is not going to be perfect. It will be off. That's what it's saying about. So your FIAE, when you take a look at it, of course it's going to be within the Runout tolerance value. Even though it isn't that perpendicular. You have a wobbling because see how it isn't that straight 90 degree down. Okay, then let's take a look at the Runout demonstration right here. So see how we put, and then that is your dye indicator, and we are going to probe it on it. See how it's rotating. So we can be able to see. Of course, this is a very exaggerated, and your measurements are, I'm going to do it again. So your measurements are captured here in your dye indicator. Of course, it's a very exaggerated animation, so your surface is like here completely off of your perpendicularity. It's too inclined. But anyway, your link is right there. You can be able to access it directly from the PDF document. Okay, now let's go into your Runout applied to the portion of that surface. So we'll go into the second next example here. So we have a chain line, which is this thick one right there, and it has its own tolerance, 0.02. This is in matrix, so we have 0 here, so 0, 1, 0, 2, your datum feature, another datum feature right there, D, okay? And this one is, of course, C. And we have our basic dimension 15 and then 3 right there. So make sure that you get the feature control frame is going to be attached to that chain line right there, and that your area to be controlled, which is this guy. is located in dimension size of that using the basic dimension for datum reference C, which is datum feature. Of course, now we're going to probe that zone. So the control zone, yeah, here limits are identified by this little yellow line right there. This is a phantom line, so you can see the individual circular elements, and our probe is right here, measurement right there, and we're taking a look at the FMI, checking that tolerance, and we're gonna do as needed verification checkpoint by using this measurement device, which is your dye indicator, so that we can be able to see these circular line elements are within the specified Runout tolerance. And again, your Runout tolerance is completely relative to this axis, which is your rotational axis anyway. So that's because it revolve, that part is going to revolve the part around that datum axis when we probe. Then let's get into the control of the circular elements by doing the outflow chart. Same thing, we're going to start looking at the surface element around a datum axis. If that's yes, if that's been applied to there, and we can take a look at is it appropriate datum axis. If that's yes, we're going to look at modifier. No, we're going to get into the datum reference. If that's yes, accept. And if it wasn't applied to the surface element around a datum axis, do not accept. And if that was applied, we're going to check if you have appropriate datum axis. If you don't have it, don't accept. And when you take a look at your Runout tolerances, that got to be applied, always applied regardless of feature size. And if you have a modifier, don't accept, because you don't need a modifier for your RFS. And then of course your Runout, we will take a look at our datum axis. If that doesn't exist, meaning like the datum axis reference in the feature control frame is no, meaning like your Runout is, your datum axis is always referenced in the feature control frame when applying Runout tolerance, meaning you can't be able to accept that, because you don't need, if you don't have it, it's impossible for us to have a circular Runout, that tolerance to control this. Okay, so this is the big picture of your decision making, going yes or no for each of the step, in order for us to decide whether that's unacceptable or acceptable. Your application of the circular Runout. Okay, then you will do your part, which is your homework. And your homework is starting from your problem 85, which is this, and I give you the answer right here for you. But make sure that you do your homework by actually doing the exercise, not just copying to turn in the assignment. If you do it all the time, you will never remember anything anyway. So total Runout, let's go into the second Runout. Total Runout again is verified by bringing a dye indicator, and then make it 90 degree, turn one 360 degree around to measure that. Alright, so we're going to go from there for your circularity, straightness, coaxiality, your angularity, your taper profile. Okay, all of them are controlled by your total Runout tolerance. So let's take a look at that. We don't need it, just read that. We will go into all the total Runout application. We don't have to say this because it's about the same thing. Okay, you will have your axis, you will have your data feature, to this one is a smaller diameter for that surface, and then of course your total Runout is on a bigger diameter, sharing the same axis right there. So you should know how to read these by now. Total Runout 0.2. Okay, so when we get to the total Runout, it should be easier for you because we have already done the circular Runout. They're about the same anyway. It's just like total is a little bit different from the circular because you're looking the entire total thing, which is all the elements on the surface of your control feature, got to be within that tolerance zone. Since it is total, we are dealing with, see, like both of the side of that diameter. So here, this is your anyway. When we say total, is like I would just say like, okay, since we're always using the datum axis as our datum feature, yeah, your total is going to be on both sides of that axis, yeah. So that's what we're talking about. In circular, if you remember, we always show only one surface, yeah, not both sides. So right now I show both sides. So meaning like, hey, go ahead and deal with this and that. Okay. All right. Now let's get into. Of course. Oh yeah, I forgot to show you the size of that is 8.5 to 8.8, and then the tolerance zone is 0.2. Okay. Now we're gonna gauge it. We use a dye indicator, put it on, and then brought into contact with this surface, and then you measure. Yeah, so the part is going to revolve, of course, around. Here is a drawing in 2D. You have already seen the animation, yeah, animated or video, so you know how we put the probe and then turn around 360 degree. So it's going to measure that, yeah, surface, total surface. Okay, so now we're gonna do the application right here. Yeah, the same thing. Of course, it's gonna go your probe. It's gonna go. You're gonna go one around 360 degree. Yeah, so make sure your surface irregularities on this surface and the surface finish. It cannot be separated. Yeah, from your Runout FMI readout. So your FMI readout, you can get it from this measurement very easily. It's automatically measuring anyway. Okay, so we're gonna diverge it, meaning like the exaggerated view. So you can see the surface right there. It's going on 360 degree around, okay? And that's your datum axis, which is this guy right there, yeah? It's just a different view, right? So your dye indicator is going to be moving in and out of that, yeah, screen. But still it is okay because it is within the acceptable tolerance zone, yeah? So your dial indicator going down. Of course, the measurement is very sensitive, so it can be able to detect, yeah, any imperfection on that surface. So that's how sophisticated the measurement verification devices are, yeah, NIST. So that's the National Institute of Standards, yeah, is taking care of all of that. All right, and then we'll get into the surface normal to your datum axis. We're going to deal with another example, of course, a different part right here. So you have your flat surface on the head of this pin, which is your locking pin. That's going to be perpendicular to that axis, yeah, and we will see if that's within the acceptable tolerance zone. Your control is a 0.004, yeah, an inch system right there. That's your total ran out, and we're going to see the perpendicular, yeah, check the perpendicular on it. All right. Then we'll get into the datum axis, yeah, and of course our datum is the primary datum here, and that's a C, and your size right here for this diameter go from 0.620 to 0.625 inches, yeah. Now we're going to put our zone as usual, and you're going to put your indicator, yeah, to find the perpendicular, to verify the perpendicularity between the surface and that axis, and go one round, yeah, and that's got to be within the two parallel planes, which is 0.004. Depends on that control frame tolerance, yeah, is 0.004 in this case apart. All right, then we're going to move our indicator. In this example, we do have the wobbling effect, meaning like the not 90 degrees straight, okay? It's just going up and down. So yeah, in this exaggerated view, we can see the imperfections right there. Yeah, how it isn't truly normal. All right. Then, of course, when you get to that point, it's going up. See, it's going up here, down, and then go up right there. So here you have your concavity. We call that kind of change in direction, yeah, on the surface. So you have either convex or concave surface, and here in this case we are detecting the concavity with this dye indicator. Okay. All right, then keep going, and let's go down again, yeah. So we're getting into the convexity, yeah. concave, and then convex. Well, you go back to your light. Yeah, in physics, we understand or trying to understand our your reflection of that, and also refraction. Yeah, so different kinds of light rays going through either a convex surface or a concave surface. You have a different images, yeah, appeared when in the back of it. So anyway, so the surface convex or the concave. So in normal word for convex, it's kind of like a turn in, yeah. So meaning the surface has turned in. Your concave is gonna be like turn out. We can also say concave like a cave, so it's kind of hollow, yeah, hollow, like that. So make sure you know the difference between the concave and the convex. International student, you can translate it, yeah, in your own language to be able to understand how that's. I can also draw that for you. So concave is, I'm gonna draw like, yeah, hollow, like that. See how the surface is hollow. That's the convex. All right, it's gonna be like this. Okay, so this is convex and that's your concave. So when you look at it, don't look at the concavity and convexity. Even though we draw like that, science is sometimes very difficult, yeah, to understand. In lens wise, yeah, we call this as a convex or converging lens, yeah, but this one is a concave or diverging lens. But then when you have to see with the surface, you are gonna cut it like that, yeah. So which is gonna give you, if I gotta draw it like this, which is gonna give you like this, okay. It's not very good to drawing, so let me just erase that. So if I have to cut it like this, you get, yeah, something like that, by the way. Okay, see that? Half of that, and that is concave, okay, hollow. And then look at that. When you cut it, you get something like that, okay? And we call this surface a convex. See, vex, meaning like it's turned in, okay, turn in. Concave is like a cave, which is hollow in, yeah. So make sure like which you're looking at. If you look at the entire body, of course, your curve, yeah, inward, your curve inward, yeah, and then your curve, this curve is outward coming out. Inward means going in, your curve, okay. So we call it a concave, and then this one is convex, okay. So concave again, and then this is your convex, okay, surface. I'm going to go ahead and erase this, okay, so you get. All right, we're going to come back into here. So you can be able to identify, okay, which one is, this one is going to be concave and that one is going to be convex. It's a little bit difficult to see how the topology of that surface changes, but of course your instrument is a very sophisticated instrument, so it can be able to sense it, all right, the surface changes. So anyway, that's your total runout. We're going to apply to the portion of a surface, and let's take a look at it. The next example, and we have a little thick line right that line, we call that the chain line, and that's your tolerance is being applied, and we're looking at our total tolerance in this case, yeah. Total runout, sorry, what am I saying? Total so total runout tolerance is 0.02, okay. And your datum, of course, a feature is your A, and your basic dimension from here to here is your 15, and here is your 6, okay. We are in the metric unit system. So it's kind of like your chain line is kind of slightly offset on one side, yeah, of your surface, meaning like this kind of like here, look at this, yeah, it's shorter than that side. So anyway, so let's go in and take a look at, we're gonna go that, yeah, total runoff for this section in that chain line. We're going to put our probe right here. Our indicator, go one round 360 degree to measure this, verify that, okay, and you can be able to get that control is going to apply only to that portion of that surface. So that's what we're talking about in this example, portion of the surface, but not the entire thing, the whole thing. So of course our checkpoint is going to check, yeah, each going in and out, the concave and convexity of that surface. And of course, in this case, we're dealing with a 0.02 for your FMI, yeah, based on that tolerance in your reference control feature control frame. Okay, and then we will get into the application check. Yeah, that's your correct application or not for your total runout control. Do the same thing. We start with our surface around the datum axis. If that is yes, we will get into datum axis. If that is appropriate, we'll go into modifier. If you don't have it, we're going to look at the datum axis. Yeah, go step by step. And if you got it, it is acceptable. If you are not applying to the surface around the datum axis, we have no business around with the total runout, so it isn't acceptable. If that was yes, we will take a look at the appropriate datum axis is identified. And if that's no, it's unacceptable, and we will go move on with the modifier. If that was yes, your modifier there isn't, we will look at the datum axis. If you don't have the datum axis, it isn't acceptable. And here is the whole picture for your decision making. Yeah, we're doing again and again the same thing, so you should get it by now to decide whether your total runout is acceptable or not in this application of that tolerance control. Okay. So now we're going to summarize the whole thing. Our runout, we have only two, your circular runout and the total runout. Circular runout is going to be your control may be applied to a feature. Total runout, your control may be applied to a feature of size. And we're going to go to number one, which is your feature control frame, okay? Your little one row table got to be applied to a feature by means of a leader. Yeah, we always put a leader to show where your tolerance is applied to, and then it is attached, yeah, to the extension line. We know that all the time. So, or it may be associated with the dimension of that size feature. Yeah, so in all cases, the meaning is the same anyway. Then we will get into and take a look at when applied to a feature or feature size like this. Okay, so size for the you will decide, yeah, each circular or the total. So it's gonna go that way, and you can be able to get your VC, which is your virtual condition, yeah, may be affected. So in this case, your runout always refers to the surface elements around a datum axis, and because of the surface to axis relationship, your virtual condition can be affected. Yeah, then we move on to the modifiers, and modifiers are not applicable because of your runout controls. Yeah. And of course, then we will look at our datum axis as we always do. Your datum axis reference is always required in the feature control frame. Modifier not applicable. You don't need it. Datum axis, you need it in order for this runout to work. Okay, then this is your homework. Your homework is going to be number 86, number 87, and number 88. The answers are given to you so you can check with it. Do not copy and give me back my own answer. Yeah, don't do that. And some of the students are doing it. I don't like it. So make sure you actually study it so you can take the test. Yeah, we have another test, test 3, and then this one is for your final portion. It's only 2 chapters, so lighter on you. Okay, that's it for the chapter 11. Yeah.